Okay, hi everyone. Welcome to the third exercise class. So the plan for the exercise class today is, because I didn't receive any particular questions about particular topics, so I'll just go through the exercises that you'll have in the exercise sheet number 3. So the first exercise there would concern Hermitian and Unitary operators. And the second exercise is like more of a fun thing of how you can use kind of the entanglements in quantum mechanics, like the superposition in quantum mechanics, to, for example, to check whether there is a bomb in a box or not. But I'll get to it. And then in the end, we maybe can have some question answer session if you have any. Okay. So let us first start with the Hermitian and Unitary operators. So like suppose that we're looking at the operator A, which acts on states in Hilbert space H, and just takes them to another state in the Hilbert space H. And there are specific cases for this operators. For example, a Hermitian operator is the operator which is equal to its conjugate transpose, which in quantum mechanics we usually write down as a dagger, as you've probably seen already in the lecture. And another special case of an operator is a unitary operator. It is such an operator such that its inverse is its conjugate transpose. So what it means is that u dagger u equals u dagger equals identity. Okay, and another object that we have already kind of touched in a previous exercise class is the exponential of an operator, or exponential of a matrix, is e to the power a, where a is the operator, and it is defined in terms of the power series for the exponential. So it's from n equals 0 to infinity, 1 over n factorial a to the power n, where a is an operator, maybe represented by matrix. Yeah, and this exercise, like in the first exercise, like if you have it in front of your eyes, that's good. But yeah, don't worry if you don't have it, if you haven't seen it yet. So in this exercise, you will look at first some properties of the operator exponentials, and also then see, and from that you'll derive how a Hermitian operator and the unitary operator can be connected. So the idea is that, so in the first part of the exercise, you have to prove that e to the power a dagger equals e to the power a dagger. Then second, you will need to see that if there are two operators a and b which commute, which means that ab minus ba equals 0, which is equivalent to just ab equals ba, which means that we can just operate with the operators as if they were just usual numbers or usual variables. And if this holds, then actually you can see that e to the power a plus b then can be just represented as e to the power a, e to the power b. Which is not that obvious, and it's not always true. So this is only true in the case where a and b commute. And third, deriving from this points 1 and 2, you have to see that if we take A, which is Hermitian, then it follows that the operator U, which we write as e to the power IA, where I is the imaginary, the complex coefficient, then this is a unitary. Okay, and you should use like this follows from 1 and 2. And then in 4, you have to prove the inverse. So if you say that if U is a unitary, then there exists A, such a Hermitian, and U equals e to the power IA. And so this 4 first points, they're actually quite similar to something that's done in analysis. So for example, I know that in some approaches to analysis, like the exponential is given initially as a power series, and actually, for example, even for real numbers, this property also has to be proved from a point of view of the power series. And the hint that I can give you in this part is that you should just use, I think it's called the Cauchy formula for when you have two, for when you have two series, at least one of which is an infinite series. Okay, and then there is also 2 more points. I'll come to them a bit later. I think like just to show you how this thing's done, I'll try to kind of derive this first property. So let us look at the e to the power A dagger. So e to the power A, we know it's expressed as the sum of the power series a to the power n dagger. Then we can take just the numbers out because they're real, and then we are left with a to the power n dagger. And here you have to remember the rules that we had for dealing with matrices. So for example, like if you do conjugate transpose of product of 2 matrices A and B transpose, then you probably remember from the linear algebra that it goes as B transpose, A transpose. So they interchange places. And this also works for, and by induction, it can be shown that like inverting this order in the product also works for the product of 3 and 4 and so on in n matrices. So essentially what happens to this product, you just have n times multiplication of matrix A dagger, then essentially, because it's all the same matrix A, what we get is A dagger to the power n. And this is exactly, by the definition, e to the power A dagger. Okay, and in the next sub exercise, you'll have to do something similar, but for the A plus B. Okay. Then there is a 4th exercise for what happens if there is an operator V, which is Hermitian and unitary, which essentially means that V dagger V equals V dagger equals 1, and V equals V dagger. Then you can prove actually that first V squared is identity. So this follows quite trivially from the 2 equations above that I've written. And the only eigenvalues that this operator can have are plus and minus 1. This you can just, yeah, to see this, you should just like write out a particular, an equation for particular eigenvalue with its eigenvector, and then act again with V or V diagonal. And the fifth one is something that I'll also derive here, also show here, so this is an equation where you have to use the Schrodinger's equation that you've seen in the lecture. And this one talks about the time derivative of a mean value, the expectation value of an operator A, which corresponds to Zurich observable. And you have to show that it can be written as follows. Okay. So here, the idea is that you have a certain observable A, which corresponds to the operator A, and then you have like a wave function which is evolving with respect to the Hamiltonian H here. So essentially, you have the Schrodinger's equation. Let me write it down. So you have the Schrodinger's equation which you've seen in the lecture, which talks about the time evolution of the wave function. And it can be written as this. So a small comment. I think like in the textbooks and also during the semester, you'll see that this constant here, h bar, is going to appear and disappear, and in some equations it might be there, in some it might not. So the idea is that this constant, it's a Planck constant, it's a fundamental constant, which is not very much of a use to us, because in our course we will not do any calculations. So in theory, when we work in theory, when we don't do any calculations, we just assume that h bar equals 1. And by the way, we also assume that c, the speed of light, if you ever see that in some equation further, it also equals 1. So this is kind of a convention that we take in theoretical physics. Like whenever it comes to the calculations, if ever you would need, you would have a need to come to the calculation. But what you do is usually you just take all these constants that you assume to be 1, and then you look at your at what you're trying to calculate, and then you see its what is its dimension, essentially. Like, is it so for example, you would need to get something which would be expressed in meters, and then what you do is just like you combine this fundamental constants in a way so that it would give you a meter, and then that is the factor that you add in front of your expression. But since in our course is theoretical, we don't need to kind of bother ourselves with the calculation of these things. So let us just assume that this constants equals 1. And if you see them by virtue of chance in some equation, for all calculating purposes, you can assume that they're 1. Okay, this was a long detour. Hope it was worth it. So we have the Schrodinger's equation, which describes the evolution of the cat of a bra, and no, sorry, it's a cat. Yeah, and then we want to write it out for a bra, right? And for this, we just need to write down the conjugate transpose, right? So, okay, so first maybe I just take I to the other side for the ket, and then I can write the equation for bra. So the Hamiltonian that governs the evolution, it's assumed to be Hermitian. So we just can write it here as this. Okay, and then what we want to calculate here is this, which is the time derivative of the expectation value of some observable A. So suppose we know how the wave function changes with time, but we want to know how the certain observable changes. So what we want to find is d by dt psi A psi. So we're taking the time derivative of all of this. And here, the trick to use is that it's very simple. So in a sense, here you have to remember that psi bra A and psi ket are actually can be seen as like separate objects, like the separate matrices. So essentially here we can just take the derivative by parts. So first we take derivative of a bra, A psi stays, then bra stays, we take the derivative of A, psi stays, and then in the end bra stays, A stays, and then we take the derivative only of ket. Okay, and for this and this, we already know the expressions which were written above here. So then we just need to substitute, and hence what we get is HA plus psi dA by dt psi minus I psi AH psi. Okay, so the first and the last terms in the expression can be written together. So what we get is HA minus AH psi plus psi this HA minus AH is exactly the commutator of H and A. So this is exactly the expression that we were supposed to get. And this is, just for your knowledge, this is actually a general case of so-called Ehrenfest theorem. We probably will see it further down the semester. So the Ehrenfest theorem is formulated for the mean values of X and P operators. But yeah, you can you can just easily get it from inserting instead of the of the arbitrary operator A, X or P operators. Oh, sorry, there was a question. Is a commutator HA just a notation for HA minus AH? Yes, exactly. This is just a notation for HA minus AH. It just turns out that the cases for which this commutator is zero can be special cases for the operators involved. Like for example, yeah, you can look at it in your spare time, but one of the properties is that if the commutator of two operators is zero, then they have the same eigenbasis, essentially. So yeah, generally it's it's a good understanding of observables and how they can relate. But in the end, it's just notation. Okay, so the RFS theorem is for X and P operators. Okay, so this was the first exercise, which is more about like you getting used to the operator notation together with a bracket notation, and also using Schrodinger's equation that you've seen in the lecture. And the second exercise is more of how we can use the superposition phenomenon that we have in quantum mechanics to perform some tasks which classically would be for which classically you would fail with certainty, essentially. And the particular experiment that we would be looking at is called Elitzur-Vaidman bomb tester. And here we also make use of the Mach-centered interferometer, which we already seen in the previous exercise sheet. So the idea of this bomb tester experiment is that, so suppose that you're given a box. And there are two options for this box. So either it's empty, so there is nothing in a box, or it contains a bomb. And the bomb is such that the bomb is very sensitive. It will explode if only hit by a single photon of light. So bomb explodes if hit by one photon of light. And your task is to determine which box you have in your hands. So task check if the box is empty or not, while staying alive, of course. Obviously, this is not achievable classically, because classically to check what's in the box, you would need to open it and or shed some light on the inside, and then if the bomb is there, then you will die. Essentially, the box will explode. However, this task is possible to achieve with high probability if we use quantum mechanical setting. And the trick to use is called interaction free measurement. So it's the idea that we kind of can probe the box with a photon of light, or not necessarily interacting with the box, which means that we just need to have a ray of light which would be in a superposition of its state. So only with some probability will it go through the box. Okay, so now let us write this down more rigorously, mathematically. Okay, so first we need to look at the single photon. So single photon, as we already seen, it can be described as two levels quantum system, and essentially a qubit is a qubit, and it's in a state psi, and for purposes here, we can just write the state as having these two components, which will be parameterized by some angle theta. So as a vector, we can write it just as cosine theta, sine theta, and we can write cosine theta 0 plus sine theta 1. Okay, and then we can look at the photon, and we can assign a certain meaning to this 0 and 1 states. So physically, what 0 and 1 states mean is actually they just correspond to two orthogonal polarizations of the photon. But I can imagine that might not say anything to you. So we can just think of it as like two different configurations of a photon. And here we can just see them as, for example, a photon traveling a top path or a bottom path. Or as in a previous exercise sheet, a photon being transmitted or reflected. So suppose that the top path we label by 0, and this is the bottom path. And the idea that initially the photon is with some probability on the top path and with some probability on the bottom path. And the amplitudes of these probabilities are the squares of the corresponding arguments in front of 0 and 1. So it will be cosine squared theta and sine squared theta. So yeah, so for here we will just take the understanding that 0 and 1 as two orthogonal states in which parameterize the Hilbert space of the photon. They just correspond to these two possible paths that the photon can take. And then what one can do is, so for a photon that we shine with a laser, so this coefficients on the path, this cosine theta and sine theta, they're just given by the laser. However, what we can do is we can adjust these amplitudes by putting a certain device on the way of the photon, which is a beam splitter. Of the two paths. By using a beam splitter. And the beam splitter action, we will denote it as U of phi. And we can see that here, cosine, maybe I'll just do this. So we have cosine theta, sine theta. Then we have the beam splitter, U of phi. And in the end, what we get is the amplitudes of two paths, they change. So that is denoted by cosine theta prime and sine theta prime. And the action of the beam splitter, U of phi, is described by the following matrix: cosine phi, minus sine phi, sine phi, cosine phi. Yeah, so this is, like if you remember from the linear algebra, this is actually the matrix for in 2D, which just carries out the rotation by angle phi. Okay, and this picture is similar to the picture that we had in a previous exercise sheet where we shined with a photon at the beam splitter, and then we had two paths that it could take. And here is the same, with only correction that here the photon does not need to arrive to the beam splitter on a particular path, like on a bottom path or on a top path, but it can be in a superposition between these two paths. Okay, and then, so we apply the action of the beam splitter to the state. So suppose this is a state psi, psi of theta. And then we arrive to a new state with the adjusted amplitudes, psi of theta prime. And now let us come to where we put the box with the bomb. So to test whether the box has a bomb or not, we just put it, so first, of course, we make like 2 tiny holes on each side of the box so that a photon can shine through. And we place it on one of the 2 paths. Let's say we place it on a bottom path. So we have a path which corresponds to 0, we have a path which corresponds to 1, and then on the bottom path, we put the box. Yeah. And we don't know, there might be a bomb, there might not be a bomb. However, we can already intuitively see that this setting is more advantageous than any classical setting, because in classical case, the only choice that we can make is to open the box, which would kill us with possibly 100% probability. But here, because we put it on a path which photon might or might not take, we still have, depending on the beam splitter that we use and the initial state of the photon, we still might have some quite high probability to survive compared to 0 probability that we would have in classical case. And if the bomb is present, then the box serves as the measurement of a state of a photon, because it would interact with the bomb inside of the state of the photon in the basis 0, 1. And outcome 1 of this measurement would mean that the photon was on a bottom path. So it would sort of collapse the state of the photon on the bottom path. And in this case, you die. And outcome 0 would correspond that the photon went through the top path, and you survive. Okay. And if there was no bomb in the box, then the measurement does not happen. Okay, so we've done with the characterizing our box with bomb or without bomb, and what it corresponds to which operations it corresponds to. So now we're ready to go to the bomb test setting, which is exactly the setting of Mach-10 interferometer. So suppose that we have an incoming photon on a top path, so in a state 0. So then we have our first beam splitter, mu of pi over 4. And this is not a great place. First, let me draw the setting, and then I write down the to which actions these things correspond to. So then we have a second beam splitter, and then in the end we have two detectors. Okay, so both beam splitters are the same, so they correspond to the action u of pi over 4. So to remind you, u of phi is this matrix. And in case of pi over 4, you would just get 1 over square root of 2, 1 minus 1, 1, 1. Yeah, so we have the setting. In the end, we have two detectors. So each detector corresponds to, wait, there was a question. Why pi over 4? Well, this is, yeah, we'll see it later. Just in calculation, actually, this is the first setting that we are considering, and the second setting that is also offered to be considered in the exercise looks at the different angle, at the different parameter of the beam splitter. Actually, it looks at the modified version of the setting where you can survive with arbitrary high probability. But for the purposes of this first introductory setting, we just use pi over 4. One can see the reason of why we use pi over 4 here to start is the following. So again, back to the setting. So I didn't finish talking about the detectors. So the detectors, there are two detectors, which the first one corresponds to the measurement in measurement of 0 state, and the second corresponds to the measurement of the state 1. So if the first detector clicks, then it's 0. If the second detector clicks, it's 1, the state 1. Okay, and we put our box with or without bomb, we don't know, on the bottom path of the interferometer. And we can see why we use u of pi over 4. So suppose we just want to calculate what is the result of, what is the state after after the first beam splitter acts on the incoming photon. So what is the state like here? So for this, we just need to act with u pi over 4 on the incoming state 0. And this is this. And this is actually, like after a simple calculation, we can see that it equals to this, which is 1 over square root of 2, 0, plus 1 over square root of 2, 1. Which means that the photon will go on the top, like on the top and on the bottom path with the same probability. So essentially, if the bomb is there, then it would only explode with a 50% probability, because the photon will go down this path only with a 50% probability. Yeah, so going from 0% probability of surviving to 50% probability is also it's an improvement. Okay, there is a question, but is the photon going any path? Isn't it going in superposition? It is not. You're completely right. The way we mathematically model it is that it's going kind of down both paths simultaneously. However, if the bomb was on a down path, the probability of it blowing up would be 1/2. And the way when I say that the photon goes the bottom path, it means that if we would make a measurement, which in this case is the bump, if we would make the measurements, then we would, and then with 50% probability, we would find it on the bottom path. Okay. Oh, okay, good. Yeah, so essentially, yeah, the setting is as follows. We shine with a photon, it goes through one beam splitter, then possibly through a bump or no bump, and then the second beam splitter, and then the measurement happens in 0-1 basis. So, like in terms of a circuit, it can be written down as follows. So we start with the 0 state, then we apply our beam splitter, and then we possibly have a measurement if there is a bump, and we have no measurement if there is no bump. And then we have a second beam splitter, and then we have a measurement again. So essentially, if there is no bump, then the measurement in the middle, it doesn't happen. So if there is no bump, the circuit just collapses to U, measurement. And if there is a bump, then there is a measurement in between. And if the measurement shows 0, then it's a top path, no explosion. It's 1, then there is an explosion. Okay, and what you have to do in the exercise, you have to analyze both of these cases, and then you'll see that the measurements, the probabilities of the measurement, of the final measurement here and here are different in the cases where there is no bump, and when there is a bump but it doesn't explode, and so on. Okay, and based on this example, like a more elaborate version of this setting can be introduced. So in a sense, this setting is already better than what we would have in classical case, as I said, because in classical case, there is we don't survive. In this case, we have a probability of 50% that if the bomb is there, then even if the bomb is there, we might survive. But 50% is still not good enough. Like it's not very comforting. And actually, this probability can be arbitrarily high. So if we consider a following setting, so we still have a photon starting in 0, but then we would use n beam splitters in a sequence. And so on. And finally the measurement 0 and 1. So we use n beam splitters here, 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 and we organize the setting in such a way so that, like, for after each beam splitter, we have the box on the bottom path. And the beam splitters that we use now would be not U of pi over 4, but U of pi over 2n. So for the case n equals 2, this exactly corresponds to the case that we've seen before. Yeah, so each one of this is here. And there are n BIM splitters. And of course, one can write down the circuit. Be U, possible measurement, U, possible measurement, and so on, U, and final measurement. And there you can also look at the cases where the bomb is in the box, where these measurements happen, and the bomb is not in the box, where this measurement don't happen, and then the probabilities of the measurement of the final measurement here would be different, and the probability of you surviving would also be higher, because what this BIM splitter does, like the previous BIM splitter, it kind of made the superposition between the top and bottom paths, it gave equal weight to the top and the bottom path, whereas this BIM splitter, it would always give the top path a higher weight than a bottom path. So the photon would always go, like if measured, the photon would always be found traveling the top path with a higher probability than the bottom path. And yeah, and in this setting, so you can guess whether the bomb is there or not with a higher probability, and you also survive with an arbitrary high probability. Like if n actually goes to infinity, then you would always survive, essentially. Okay, so these were the two exercises in the next exercise sheet. And I think since I don't have anything else for today, yeah, I'll finish with my presentation, and now we can go to the questions that you might have for the other exercises or for the lecture, for example. Yeah, so feel free to shoot. Okay, if there are no questions, then I think that's it for today. So one remark: if there is a particular topic that you would like to discuss more, like in more detail, like on one of the exercise classes, if there is something not extremely clear in the lecture and so on, then please write me an email, and I can dedicate part of the exercise class to discussing this particular topic. Also, if there is something mathematical that you don't understand, or you maybe didn't have in your courses before, then yeah, we can also discuss that. Oh, there's a question. So, okay, the question about the last exercise: doesn't a bit flip require both a transition from 0 to 1 and other way around? Yes, you're right. The the question was about actually, I think I have it open here. Yeah, so the question was, what is the duration of a pulse needed to create a superposition, implement a Hadamard gate, or perform a bit flip. Yes, you're right. So here, what I meant is more like if we start from a 0 state, what do we do to get to the superposition or a bit flip from 0 to 1? Yes. So the transition, like the operator which performs the transition from 0 to 1, like it's not the same operator which performs the transition from 1 to 0. Like in this rotational picture. So if you had given just the operators, if you have just found the operators which perform the transition from 0 to 1 or from 0 to the 1 over square root of 2 0 plus 1, then that's already kind of a good answer. To be completely clear with this question is actually there exists an operator which corresponds to the bit flip or to the Hadamard gate. But this operator would correspond to the sequence of transitions. So you would first need to do one pulse, then probably change the phi and do another pulse and so on. And generally, I think like a good remark is also that like if there is any gate, any 1 qubit gate, let's call it, I don't know, U. It can always be represented as a product, I think, of 3 transitions. So this is just a remark, essentially. So geometrically, you can see it as if you have a state on the sphere, you have a point on the sphere, you can perform 3 rotations, essentially, to 3 or 2 rotations. Yeah, probably even two rotations to get to that point. And let me think, 3 or 2? It's a good question. Yeah, anyway, so you can always represent going to the point on a sphere by a sequence of doing rotations around x, y, and z. And hence, like every single qubit gate can be represented as a sequence of these transitions. But concerning the exercise, yeah, your remark is completely right. So the gate which performs transition 0 to 1 does not perform transition 1 to 0 in this case. But a sequence of gates can. Yeah, maybe like if this topic comes up. So just to give you a bit of intuition, and this is something that actually I think a couple of lectures in the quantum information processing course are dedicated to. So actually the general idea is not really given in respect to only 1 qubit gates. So for 1 qubit gates, we can say that we can represent it as as a sequence of these rotations. Then the next step is that saying that, oh, if we have a 2 qubit gate, then we can represent it as some sequence of rotations on a single qubit and a number of C0s. So just for example. So H2 qubit gate you can just represent as a combination of C0s and 1 qubit gates. Then for 3 qubit gates, you can say that you can always represent it as a combination of 2 qubit gates, 2 qubit gates and single qubit gates. And for each 2 qubit gate, you already know that you can represent it as a single qubit gate and a C0. So and in the end, by induction, you can get to the point that if you have an arbitrary number of qubits and you have like this huge unitary gate acting on all of them, you can decompose this huge gate into just single qubit gates and CNOTs. It could be a huge circuit, but you can do it, like just by brute force of decomposing it. And yeah, there is also a theorem on the number of this CNOTs and single qubit gates, which you would need to decompose an arbitrary unitary. And subsequently, there is also a subfield of quantum computing, which is dedicated to finding optimal ways to decompose a given unitary into single qubit gates and CNOTs. So I don't know if it will come to that, but maybe you'll have something like this as an exercise in one of the future exercise sheets. Or alternatively, this would definitely come up in the quantum information processing course. So like if you're further interested in that, then you can also take it next semester. Okay, the question. Okay, so the question is, would it be possible to activate the Moodle forum for questions about the lectures? It's not activated. Okay. Okay, I'll try to tweak the settings now. I thought it should have been activated, but yeah, let me know if it doesn't work. Just write me an email. Also, the question I posted yesterday on YouTube, when deriving the canonical commutation relation, it seems that psi is an eigenstate of operator X, but I don't see why that would be the case in general. Okay, I haven't seen the lecture, but yeah, but I can see. So maybe my way to answer it would be that, like, whenever we act with an operator, whenever we choose a state to act with an operator, we usually choose the eigenstate for the reason that if you take an arbitrary state, then an arbitrary state you can write just as a superposition of the eigenstates, like just as a linear combination of the eigenstates. And then essentially, the way you would act on an arbitrary state would just correspond to the linear combination of acting on the eigenstates in its decomposition. And so to understand how the state is acting on how the operator is acting on arbitrary state, it's enough to understand how it's acting on the eigenstate. Is that, does it answer the question? Okay. Any more questions? Okay, then yeah, you can always write me an email. Yeah, thank you for attending. Yeah, see you next week or on question and answer session on Tuesday.